From the elite coastal enclaves of Naples to the sprawling master plan developments of Orlando, outdoor living is a high-stakes investment. Right now, thousands of these luxury estates are equipping their pool decks with motorized retractable screens. While marketed as simple, automated lifestyle enhancements, these systems function as complex, dynamic architectural facades. The peninsula's geography requires any exterior addition to constantly negotiate severe aerodynamic loads. The wind pressures generated by localized thunderstorms and cyclonic activity test the absolute physical limits of these structures. This stress is compounded by a constant attack of airborne coastal salinity and intense thermal cycling that bakes anything exposed to the Florida sun. Treating these highly tensioned, motorized barriers as simple outdoor appliances invites rapid mechanical degradation. Without rigorous engineering, the result is catastrophic failure and severe property damage. A dangerous misconception exists in the current market: the idea that standard motorized insect or solar screens provide inherent storm protection. They do not. Under the Florida Building Code, standard motorized screens are officially designated as Risk Category I structures. This low-hazard classification is reserved for buildings that represent a minimal risk to human life in the event of failure, alongside agricultural facilities and minor storage structures. Identifying a survivable system requires analyzing precise aerodynamic thresholds and the specific material sciences that prevent rapid mechanical degradation. A screen system becomes a structural liability if it is not engineered to exact climate-specific tolerances. The structural vulnerability begins with a regulatory provision known as the Screen Removal Alternate Method. Under Chapter XXX of the Building Code, contractors may engineer the primary aluminum framework of a pool cage or lanai on the mathematical assumption that the screen panels will be fully retracted during high wind events, allowing air to pass cleanly through. The code strictly stipulates that these standard panels must be rolled up whenever forecast winds are expected to exceed 75 miles per hour. If a standard screen remains deployed during a low-level Category 1 hurricane, the tightly woven fabric reacts to wind speeds as low as 74 miles per hour. This diagram illustrates the sail effect. When a deployed screen captures heavy wind, it transfers that energy as twisting torsional force into the aluminum structure. Because the architecture assumes air will pass through, this load can buckle vertical columns or collapse the entire lanai. The disparity in load tolerances is significant. Standard zipper insect screens tear at 50 miles per hour, below the 75 mile per hour retraction limit. True survival requires Kevlar aramid fibers and welded end retention systems certified for Category 5 impacts of 156 miles per hour. Marketing non-Kevlar screens as storm barriers ignores these structural mathematics and creates a severe physical and legal hazard for the property owner. Aerodynamic stress leads directly to the physics of the mesh itself. Modern architectural screens typically rely on one of two foundational materials: woven fiberglass yarns coated in PVC or high-tenacity polyester fibers coated in PVC. Fiberglass mesh offers high dimensional stability. It resists stretching over time, making it preferred for spanning massive horizontal openings. Conversely, PVC-coated polyester provides extreme tensile strength and elasticity, which is necessary for active environments dealing with direct physical impacts. Some manufacturers integrate solid, clear vinyl windows into these mesh systems. However, clear vinyl undergoes substantial thermal contraction in lower temperatures, constricting with enough force to warp the aluminum tracks or tear horizontal seams. The structural integrity of the mesh often comes down to the methodology used to attach the retention zippers. Budget manufacturers routinely rely on traditional industrial sewing machines for this connection. Sewing requires high-speed steel needles to punch hundreds of holes per linear foot straight through the polymer fabric. This creates a continuous line of structural weakness, exactly where the fabric experiences its highest lateral tension. Furthermore, conventional nylon or polyester threads succumb rapidly to UV radiation and intense coastal humidity, resulting in accelerated thread rot. As the screen travels through its tracks, physical abrasion snaps the rotting thread. Once the stitches fail, the zipper separates from the fabric, allowing the edge of the screen to pull out of the track and flap in the wind.
High-frequency heat-welded seams are an engineering imperative. This process fuses the zipper to the mesh, ensuring the fabric maintains its tensile integrity under aerodynamic stress. This schematic details the 3 primary stress vectors attacking the internal electromechanical architecture hidden inside the sealed overhead aluminum housing. During the summer, direct solar radiation turns that sealed housing into an oven. Internal temperatures easily exceed ambient levels, leading to rapid thermal degradation of the plastic gears and printed circuit boards in budget motors. There is also an operational hazard during cyclonic events. Hardwired smart screens rely on a power grid that frequently fails during Florida storms. Without manual override cranks specified at the design phase, screens become trapped in the deployed position as storm winds rise. Even when the grid is stable, mandated exterior ground fault interrupter outlets present a persistent nuisance, frequently tripping during heavy wind-driven rains and cutting power to the system. Airborne coastal salinity provides an electrolyte for chemical attack. On substandard hardware, salt crystals gather on threads and rapidly bloom into dark rust. As indicated in the upper section of this engineering cross-section, that weeping rust leads to galvanic fastener corrosion, eventually seizing the internal roller bearings. Finally, the lower section highlights the biological threat. Facade, or mud daubers, frequently bypass poor end cap tolerances to build concrete-like mud nests directly on the roller tube. Retracting the screen over these nests causes fabric punctures and electrical fire hazards. Preventing rapid mechanical degradation requires specifying marine-grade 316 stainless steel hardware, intelligent motor technology, and committing to exhaustive preventative maintenance. Physical mechanical failure is only the first layer of risk. In Florida, the structural viability of a screen is inseparable from the highly litigious matrix of municipal building codes and homeowners association covenants. The legal landscape shifted under Florida House Bill 293. As shown on the left, HOAs no longer possess authority to outright deny impact-rated Kevlar systems. However, standard screens remain vulnerable. HOAs retain broad exclusionary powers to deny non-hurricane installations based on subjective aesthetic preferences. Furthermore, permanent motorized installations require formal municipal building permits and CRC-certified engineering stamps to prove structural compliance. As the warning box details, unpermitted work triggers severe consequences. Municipalities may issue stop work orders, levy steep fines, and force complete equipment teardowns. Navigating community architectural boards requires applications built specifically around documented structural safety and the protection of neighborhood property values. The high upfront capital expenditure of a custom installation is merely a fraction of the total cost of ownership. Long-term survival demands an end-user commitment to specialized maintenance protocols, including the regular application of dry PTFE lubricants and freshwater washdowns to mitigate salt air corrosion. True outdoor luxury in Florida requires refusing any compromise on structural integrity. Only meticulously engineered systems will survive the environment they were built to control.